Let's explore the process of converting a non-deterministic finite automaton, or NFA, into a deterministic finite automaton, or DFA, using the subset construction algorithm. We're essentially transforming a non-deterministic machine into a deterministic one. Before diving into the conversion, let's highlight the key differences between NFAs and DFAs. An NFA allows for multiple transitions from a single state for a given input, indicated by the multiple transition symbol, and it can have epsilon transitions, represented by the lightning symbol, meaning it can change states without consuming any input. This makes the NFA non-deterministic, marked by the target symbol. On the other hand, a DFA has only a single transition for each state and input symbol, shown by the right arrow symbol. It does not allow epsilon transitions, indicated by the no symbol, making it deterministic, marked by the check mark symbol. The subset construction algorithm is the method we use to convert an NFA to a DFA. The core idea is that we create DFA states from subsets of NFA states. Each state in the resulting DFA corresponds to a set of possible states the NFA could be in after processing a given input. The conversion process consists of 4 main steps. First, compute the epsilon closure of the NFA's start state. Second, create the initial state of the DFA using this epsilon closure. Third, for each state in the DFA and for each input symbol, compute the transitions to new DFA states. Fourth, identify and mark the final states in the DFA. A DFA state is considered final if it contains any of the final states of the original NFA. Epsilon closure is a crucial concept in this conversion. The epsilon closure of a state is the set of all states reachable from that state by following only epsilon transitions, including the state itself. The formula for epsilon closure of a state Q is epsilon closure of Q equals the set containing Q, union with all states reachable via epsilon transitions. Here is a snippet of code to illustrate the algorithm's implementation. We define a function NFA_to_DFA that takes an NFA as input. It initializes the DFA with the epsilon closure of the NFA's start state. The code then iterates through the states of the DFA, and for each symbol in the alphabet, it computes the next states using the move function, followed by calculating the epsilon closure of these next states. If this closure is not already in the DFA states, it's added. Let's consider an example NFA. The diagram consists of 4 states: Q subscript 0, Q subscript 1, Q subscript 2 and Q subscript 3, with Q subscript 0 being the start state and Q subscript 3 being the final state. There is a transition from Q subscript 0 to Q subscript 1 on input A, an epsilon transition from Q subscript 0 to Q subscript 2, and transitions from both Q subscript 1 and Q subscript 2 to Q subscript 3 on input B. The language recognized by this NFA is A followed by B, or epsilon followed by B, in other words, the set of strings ending with B. To summarize, subset construction algorithm creates a DFA that is equivalent to the original NFA. Epsilon closure is essential for handling epsilon transitions in the NFA. Each state in the DFA represents a set of states from the NFA. Most importantly, the resulting DFA and the original NFA recognize the same language. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.